Welcome! In this video, we will show you how you can use Scheduler 7.5 to effectively optimize productions with stockpiles. We'll explore an iron ore project that utilizes various processes and stockpile reclaim methods. You'll learn effective strategies for managing capacity and movements within ROM pads while maintaining stockpile segregation to meet production requirements. Join us as we dive into these techniques to optimize mining operations. Stay tuned until the end to discover how you can leverage stockpile expansions to maximize your net present value. Let's have a look at this project's setup. When the ore is mined, the higher grade ore is sent directly to the direct shipping ore (DSO) process to crush and screen. But the lower grade ore is first stockpiled before it is reclaimed to crush and concentrate in a beneficiation plant. Multiple stockpiles will be used to store different grades of iron and phosphorus to provide a steady supply of ore to the beneficiation plant. To model this in Scheduler, the mining process is split into beneficiation plant and DSO. These processes are further separated into different product options, and then multiple products are blended to form the final product. Let's have a look at how we would set up the base scenario. We'll limit the amount reclaimed for the beneficiation plant to a maximum of 10 million tons. The direct and reclaimed material to DSO will be capped at 15 million tons. Total products will all be kept at 15 million tons per time period with iron level between 59 and 63%. In LOFOs the level of phosphorus will be under 0.08% and will get $115 per ton in revenue. In MIDFOs, it will be between 0.08 and 1% for $105 per ton. In HIFOs, it will be between 0.1 and 0.12% for $95 per ton. We will use these financial and constraint values for setting up all our scenarios in this project. Let's see how we would model that with process and attribute constraints. To prevent the beneficiation plant from receiving direct input from the mine, set the maximum direct material to Baini plant to 0. Set the maximum reclaim amount for Baini plant to 10 million tons a period. Then we just need to set the process and attribute constraints according to our project requirements. Let's quickly set the DSO and total products to 15 million tons, the level of iron in all total products to be between 59 and 63 and phosphorus limits for HIFOs, MEDFOs, and LOFOs. Let's set a limit on the pit group as well to reduce variability in mining. Let's check our optimization settings to make sure we have enabled stockpile and reclaim. As we are optimizing with stockpile reclaim, you will need to use either forward or sliding window optimization strategy. We will use sliding window, and let's tick stockpile and reclaim. Let's optimize our first scenario. As you can see from the movement chart, the amount reclaimed for the beneficiation plant satisfies the maximum throughput of the plant. However, looking at the stockpile chart, a large amount of material is stockpiled. This might not be ideal where storage space for stockpiling is limited. We'll now show you how to upgrade your model and scenario to improve this. Let's revisit our material flow diagram. We want to model these stockpiles as fingers on ROM pads based on their level of phosphorus, so let's group them in ROM pads called High P, Med P, and Low P. We will group all of them together as total ROM. We can now vary stockpile capacity using constraints to model stockpile formation, expansion, drawdown, and closure. So, let's model the next scenario as follows. We will limit High P to a constant capacity of 10 million tons per period. Let's allow Low P ROM formation to start in period 2, and we will limit it to 5 million tons per period from then on. For Med P, we will start it like Low P, but we will also expand the capacity to 10 million tons from period 5 onwards. How about we set an overall stockpile capacity limit of 15 million tons on the total ROM and close the stockpiles by the last period? Let's go back to Scheduler to see how we can do this. We have already defined individual stockpiles with different levels of iron and phosphorus. To model them as fingers within ROM pads based on the level of phosphorus, you just need to group them together in the pads that they belong to. Let's create High-Phos stockpile group, enter high P in the search box and add these as fingers into the high phosphorus group. Do the same for Med-Phos. Create Low-Phos. Tick the unallocated checkbox this time and just add all the stockpiles remaining. Create a total ROM stockpile group to control the overall stockpile capacity or movements. Now that we have grouped these stockpiles, we want to put a capacity limit on each of them. Let's clone our base scenarios. Just like the pit and dump locations and group, you can find it in the Locations tab. Add the stockpile capacities as we have discussed earlier. Let's put a stockpile group filter on the constraint type so that we can just focus on our stockpile group constraints. Let's optimize again. The stockpile levels are looking more reasonable now. But, looking at the stockpile movements, they are exhibiting significant variability. Let's add some controls on the movements in and out of stockpiles. Just like pit and dump constraints, you can set minimum, maximum, cumulative, and difference constraints on materials going in and out of stockpiles and stockpile groups. For the next scenario, we'll only show you how to control the stockpile movements using the basic minimum and maximum constraints. We want to stockpile at least 1 million tons of high phosphorus materials in high P ROM pad in the first period, but we only want to reclaim that from period 5 onwards. Let's limit the reclaim of low phosphorus material from low P ROM pad to a maximum of 2 million tons per period. Let's optimize again. Okay, let's check the charts again. We can see from the high P ROM chart that 1 million tons of high phosphorus materials are stockpiled in period 1 and they are only reclaimed from period 5 onwards. Looking at the amount reclaimed from low P ROM pad, it has hit the limit of 2 million tons quite often. We want to see if it is viable to increase the limit. Instead of changing the reclaim limit directly, we can model this via capital expenditure. So, for our last scenario, we shall explore the use of capital expenditure in maximizing the true net present value of stockpile movement. Let's clone our last scenario. This time, we will go over to Financials Capital Expenditure to add a new capital expenditure. Let's just say it will cost an extra $1 million to move 1 million tons of ore, and we allow it to be incurred up to 5 times. Okay, let's optimize again. Looking at the low P ROM chart again, we can see that it has incurred the capital expenditure to increase the reclaim from low P. So, that's it. In this video, we have discussed how you could group your stockpiles to have macro-level control of your stockpile operations. We have demonstrated the use of capacity and movement constraints as well as capital expenditure on your stockpile groups. You can quite easily apply similar constraints to individual stockpiles as well. I hope this video has been helpful in showing you how you could use Scheduler to effectively optimize your productions with stockpiles.